Let's start with something truly bizarre. Imagine a cat in a sealed box. Inside this box, along with the cat, is a fiendishly clever device, a radioactive atom, a Geiger counter, a hammer, and a vial of poison. Here's the setup. The radioactive atom has a 50% chance of decaying in the next hour. If the atom decays, the Geiger counter detects it, triggering the hammer, which smashes the vial of poison, killing the cat. If the atom doesn't decay, the cat lives. Now here's the crucial question. After 1 hour, is the cat alive or dead? Your immediate instinct is probably to say, well, obviously it's either alive or dead. We just don't know which. But according to the standard interpretation of quantum mechanics, the theory governing the behavior of matter at the atomic level, the answer is far stranger. Before we open the box, the cat is neither alive nor dead. It exists in a superposition of states, a bizarre quantum limbo where it is simultaneously both alive and dead. It's only when we open the box and observe the cat that the superposition collapses, forcing the cat to choose a definite state, alive or dead. This thought experiment, known as Schrödinger's cat, was devised by Erwin Schrödinger in 1935 to highlight what he saw as the absurd implications of quantum mechanics when applied to everyday objects. It's a paradox that continues to baffle and fascinate physicists and philosophers to this day. The reason this matters, the reason Schrödinger bothered dreaming up this macabre scenario, is that it forces us to confront the fundamental nature of reality. It suggests that observation plays a crucial role in determining what is real, and that until we observe something, it exists in a blurry probabilistic state. And if that's true for a cat in a box, what does it mean for us? What does it mean for our very existence? This leads us to the idea of quantum immortality, which suggests that because the universe is constantly branching into multiple possibilities, there's always a universe where you survive, even in situations where death seems inevitable. It's a mind-bending concept, to be sure, and one that requires us to delve deep into the strange and wonderful world of quantum mechanics. If you're enjoying this journey into the quantum realm, hit that like button and subscribe so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city and time zone you're watching from. There's something special about knowing this story is reaching people all over the world. Over the next chapters, we will explore this idea. First, we need to understand the basics of quantum mechanics. We'll start by examining what quantum mechanics is and its history. Then we'll talk about what it means for the universe, and then we'll dive deep into quantum immortality. So, what exactly is quantum mechanics? In essence, it's the theory that describes the behavior of matter and energy at the atomic and subatomic level. It's a world where the rules of classical physics, the physics of everyday experience, break down. Think about it this way. In classical physics, objects have definite properties. A baseball has a definite position and a definite velocity at all times. You can, in principle, predict its trajectory with perfect accuracy, given enough information. But in the quantum world, things aren't so clear-cut. Particles like electrons don't have definite positions or velocities until we measure them. Instead, they exist in a state of probability, described by a mathematical function called a wave function. This wave function tells us the probability of finding the particle at a particular location or with a particular velocity. This isn't just a matter of not having enough information. It's not like the baseball being hidden behind a curtain. The electron literally doesn't have a definite position until we measure it. The act of measurement forces the electron to choose a definite state. This is where things get really weird. Before measurement, the electron exists in a superposition of all possible states. It's like it's in multiple places at once. It's only when we measure it that the superposition collapses and the electron decides to be in one particular place. To understand why this is so revolutionary, consider the famous double-slit experiment. In this experiment, Electrons are fired one at a time through a barrier with 2 slits in it. On the other side of the barrier is a screen that detects where the electrons land. If electrons behaved like classical particles, you'd expect them to pass through one slit or the other and create 2 distinct bands on the screen. But that's not what happens. Instead, the electrons create an interference pattern, a series of alternating bands of high and low electron density. This interference pattern is exactly what you'd expect if the electrons were behaving like waves. But electrons are particles, right? Well, in the quantum world, they're both particles and waves. This is known as wave-particle duality, and it's one of the most fundamental and mind-bending concepts in quantum mechanics. Each electron goes through both slits at the same time. They interfere with themselves. The implications of this are profound. It means that the very nature of reality is probabilistic and uncertain at the quantum level. It means that observation plays a crucial role in shaping what is real. And it means that the universe is far stranger and more mysterious than we ever imagined. Now, let's delve a little deeper into the mathematical framework that underpins quantum mechanics. The key concept here is the wave function, often denoted by the Greek letter psi, p. The wave function is a mathematical description of the quantum state of a particle. It encapsulates all the information we can possibly know about the particle's properties, such as its position, momentum, and energy. But here's the catch. The wave function itself doesn't directly tell us the particle's position or momentum. Instead, it tells us the probability of finding the particle at a particular location or with a particular momentum. To get this probability, we need to square the absolute value of the wave function. This gives us the probability density, which tells us the likelihood of finding the particle in a given region of space. This probabilistic nature of quantum mechanics is enshrined in the Heisenberg uncertainty principle. This principle states that there's a fundamental limit to how precisely we can know certain pairs of physical properties, such as position and momentum. The more accurately we know the position of a particle, the less accurately we can know its momentum, and vice versa. Mathematically, the uncertainty principle can be expressed as dex dep 2, where dex is the uncertainty in position, dp is the uncertainty in momentum, and h, pronounced Haybar, is the reduced Planck constant, a fundamental constant of nature. This isn't just a limitation of our measurement techniques, it's a fundamental property of the universe. The universe is, at its core, uncertain. Now, how does the wave function evolve over time? The answer is given by the Schrödinger equation, a cornerstone of quantum mechanics. This equation describes how the wave function changes in response to the forces acting on the particle. Solving the Schrödinger equation allows us to predict the future behavior of the particle, albeit in a probabilistic sense. But here's something else that gets strange. Before measurement, it can be thought that the particle is in multiple places at once, and that each of the places is a possible future. The act of measurement collapses the superposition. This brings us back to Schrödinger's cat. Before we open the box, the cat exists in a superposition of alive and dead states. Its wave function is a combination of 2 wave functions, one representing a living cat and one representing a dead cat. It's only when we open the box and observe the cat that the superposition collapses, and the cat chooses to be either alive or dead. We've seen the weirdness that is quantum mechanics, how probabilities are not just our ignorance but the nature of reality, how observation plays a key role in the outcomes. Next, we'll delve into the many worlds interpretation of quantum mechanics, which takes this idea to its logical extreme, suggesting that every quantum measurement causes the universe to split into multiple parallel universes. Okay, buckle up. We've only just scratched the surface of the quantum rabbit hole, and it's about to get a whole lot deeper. We're talking about the many worlds interpretation MWI and its bizarre offspring, quantum immortality. Remember Schrödinger's cat, that poor hypothetical feline trapped in a box with a radioactive atom, a vial of poison, and a whole lot of existential dread? The traditional Copenhagen interpretation of quantum mechanics, the one most physicists reluctantly accept, tells us that the cat exists in a superposition, both alive and dead, until we, the observers, open the box and peek inside. Poof! The act of observation forces the wave function to collapse, and the cat's fate is sealed. It's either a living, breathing ball of fluff or a tragically deceased one. End of story, relatively speaking anyway. But the many worlds interpretation throws a wrench into that tidy little narrative. It boldly proclaims, hold on a second, what if the wave function doesn't collapse? Instead of collapsing into a single definite outcome, MWI proposes that the universe does something far more dramatic. It splits. When we open the box, the universe doesn't just decide whether the cat is alive or dead. Instead, it bifurcates, branches, diverges into two distinct, equally real realities. In one, you, with a mixture of trepidation and morbid curiosity, open the box and find a living, purring feline. Perhaps a little perturbed by its confinement, but otherwise perfectly fine. In the other, you open the box and find, well, a less lively feline, perhaps a bit stiff. Both realities, according to MWI, are equally real, equally valid. They simply exist in parallel, forever separate, like two paths diverging in a quantum wood. Think of it like a colossal, ever-expanding, branching tree, its roots buried in the bedrock of the Big Bang. Each time a quantum event occurs, a radioactive atom decaying, an electron passing through a slit in a double-slit experiment, a cat's life hanging precariously in the balance, the universe sprouts a new branch. Each branch represents a different possible outcome of that event, an alternate reality where that particular possibility became actualized. An infinite forest of possibilities, constantly growing, constantly diversifying. Dr. Eleanor Vance, a theoretical physicist at the forefront of MWI research, often used this analogy in her lectures. Imagine, she'd say, her eyes gleaming with intellectual fervour, every decision, every quantum event as a fork in the road. We only experience one path, but the others are still there, just out of reach, shimmering like mirages in the distance. So, what does this mind-boggling cosmic branching have to do with living forever, had you asked? Because this is where things get really interesting. Let's imagine a slightly more robust scenario than a cat in a box. Let's say you are participating in let's call it a high-stakes experiment. You've volunteered, or perhaps been volunteered, the details are murky, for a project that pushes the boundaries of quantum possibility. You're placed in a sterile white room. The air hums with the low thrum of sophisticated machinery. Before you stands a device, sleek and ominous, that has a 50% chance of killing you and a 50% chance of leaving you unharmed. The device operates based on a quantum event, say the decay of a radioactive atom. A Geiger counter clicks rhythmically, measuring the atom's activity. If the atom decays within a certain precisely timed interval, the device triggers, and, well, let's just say the outcome is not conducive to continued existence. If it doesn't decay, you walk away scot-free, a little shaken perhaps, but very much alive. According to the Copenhagen interpretation, after the device is activated, after the Geiger counter has made its fateful pronouncements, you'd either be alive or dead. Simple, right? Morbid, utterly terrifying, but simple, a binary outcome. But according to MWI, something far more peculiar, more unsettling happens. The universe splits. In one branch, the atom decays, the device triggers, whatever that trigger entails. Let's not dwell on the specifics. And you cease to be. Your consciousness flickers, then vanishes like a candle snuffed out in a hurricane. But in the other branch, the atom stubbornly refuses to decay. The device remains dormant, and you're still alive and kicking, perhaps sweating profusely and questioning your life choices, but undeniably, unequivocally alive. Now, here's the kicker, the truly mind-bending twist. From your perspective, you only ever experience the branch where you survive. Why? Because, well, you can't experience being dead. If you're dead, there's no you to experience anything. The lights go out. The curtain falls. End of story. In the branch where you die, your consciousness ends. That's it. Game over. A permanent, irreversible cessation of being. But in the branch where you live, your consciousness continues blissfully, or perhaps anxiously, oblivious to the fact that a version of you just bit the dust in another reality, another branch of the ever-expanding cosmic tree. And this, my friends, is the essence, the seductive allure, the terrifying promise of quantum immortality. Every time you face a life or death situation governed by quantum mechanics, the universe splits. In some branches you die, no doubt about it. The odds might even be stacked against you in many of those branches, but in at least one branch you survive. And because you can only experience the branches where you survive, you effectively continue to exist, hopping from one reality to the next, always narrowly escaping death, like a cosmic cockroach scuttling from one disaster to another. It's not immortality in the traditional mythical sense. You're not becoming invulnerable, ageless, immune to the ravages of time and entropy. You're still susceptible to accidents, diseases, and the eventual heat death of the universe. You'll still age, still suffer, still experience loss, but from your subjective point of view, you never experience death itself. You simply keep waking up in realities where you miraculously survive the latest quantum gamble, the latest roll of the cosmic dice. Mind-blowing, isn't it? Or perhaps just utterly bonkers. Now, before you start volunteering for dangerous quantum experiments, before you start playing Russian roulette with radioactive isotopes, let's address some crucial, sobering caveats. First and foremost, this is all highly theoretical, speculative, bordering on science fiction. There's no concrete empirical evidence to definitively prove that the many worlds interpretation is correct, let alone that quantum immortality is a real, verifiable phenomenon. It's a thought experiment, a way to explore the logical implications of quantum mechanics, to push the boundaries of our understanding, and to grapple with the profound mysteries of existence. It's a playground for the mind, not a blueprint for eternal life. Second, even if MWI is the correct interpretation of quantum mechanics, even if the universe is constantly branching into countless realities, quantum immortality doesn't guarantee you're going to live a long, happy, fulfilling life. It just means you'll never experience death from quantum events. You can still die from a car accident, a heart attack, a stroke, a falling piano, or any other multitude of non-quantum causes. In fact, the vast majority of ways you could potentially die probably aren't governed by quantum mechanics. You're more likely to be hit by a bus than killed by a radioactive decay. Third, and perhaps most importantly, let's consider the elusive, enigmatic nature of consciousness itself. For quantum immortality to work, consciousness needs to be something that can transfer or persist across these branching realities. It needs to be able to somehow choose the reality where it continues to exist. But what is consciousness? How does it arise from the complex interplay of neurons in the brain? And how does it interact with the quantum world? These are all open questions, fundamental mysteries that we don't have definitive answers to. We'll need to explore the intricacies of the observer effect in far more detail to even begin to understand the relationship between consciousness and quantum reality. Think about it. If consciousness is simply an emergent property of the brain, a complex illusion created by the firing of synapses, and the brain is irrevocably destroyed in one branch of the universe, what happens to that consciousness? Does it simply cease to exist like a melody cut short? Or does it somehow migrate to another branch where the brain is still functioning, like a song carried on the wind? These are deep, profound philosophical questions that delve into the very nature of existence, the very essence of what it means to be, and they were absolutely crucial to understanding the potential or lack thereof of quantum immortality. So, is quantum immortality a real possibility? A tantalizing glimpse into a potentially infinite existence, or just a fascinating, albeit unsettling thought experiment? A product of our overactive imaginations? The jury's still out. But exploring these ideas, grappling with these concepts, forces us to confront some of the most profound mysteries of the universe, pushing us to question our most fundamental assumptions about reality, consciousness, and the very nature of life and death. It compels us to look beyond the comfortable confines of our everyday experience and to contemplate the truly bizarre and wondrous possibilities that lie hidden within the quantum realm. In the next chapter, we'll delve even deeper into the observer effect and its profound implications for quantum mechanics and the nature of reality. We'll explore how the very act of observation seems to fundamentally alter the behavior of quantum systems, how the presence of a conscious observer appears to collapse the wave function and force a quantum system to choose a definite state. And of course, we'll consider how all of this might relate to our understanding of consciousness, the many worlds interpretation, and the tantalizing, elusive possibility of quantum immortality. Get ready to have your mind blown all over again, and maybe bring a towel. Things are about to get messy. Okay, Elias began, pushing his glasses up his nose, the gesture more habitual than necessary. The lenses were already perched perfectly. Let's dive deeper into this quantum rabbit hole. We've skirted around it, tiptoed near it, but now it's time to really confront the observer effect. What is it? Why does it matter? And how does it fuel the flames of quantum immortality? He paused, letting the weight of the question hang in the air of his cluttered office, a sanctuary of half-empty coffee cups and stacks of physics journals threatening to topple at any moment. Across from him, Sarah leaned back in her chair, a skeptical glint in her eye. She was a pragmatist, a biologist by training, and while she found Elias's theories fascinating, she also considered them dangerously close to bordering on science fiction. Elias, with all due respect, I still think this is a bit out there. Quantum immortality. Really? He chuckled, a warm, rumbling sound that filled the small space. Out there, perhaps, but not impossible. And understanding the observer effect is key to even beginning to grasp the concept. He swiveled in his chair, reaching for a whiteboard marker that was inevitably capped on the wrong end. He uncapped it with a frustrated sigh. "Remember Schrodinger's cat?" he asked, already sketching a crude outline of a box. "Poor feline trapped in a box, both alive and dead until we peek inside. That peeking inside is the observer effect in action. In the quantum realm, the very act of observing a system fundamentally changes it. It's not like watching a bird in your backyard. You see the bird, but your observation doesn't alter its behavior usually. With quantum particles, observation forces them to choose a state." Sarah frowned. "But that's just a thought experiment, Elias. Schrödinger himself designed it to illustrate the absurdity of applying quantum mechanics to macroscopic objects." "True," Elias conceded, drawing a sad-looking cat inside the box. "But the principle remains. The cat theoretically exists in a superposition of states, alive and dead, until the box is opened. The act of opening the box, of observing, forces the cat to collapse into one state or the other." He tapped the whiteboard with the marker. "Think of it like this. Before we open the box, the universe holds both possibilities. After we open it, only one remains, from our perspective." He moved on to the double-slit experiment, sketching 2 vertical lines on the whiteboard. Think back to the double slit experiment. When we don't observe which slit the electron passes through, it acts like a wave, creating an interference pattern. He drew the characteristic wave pattern on the board, but the moment we try to catch it in the act, the wave collapses and the electron behaves like a particle going through one slit or the other. He drew the particle pattern, 2 distinct lines. The interference pattern vanishes. Poof! He made a sweeping gesture with his hand as if magically erasing the wave pattern. Sarah leaned forward, her skepticism momentarily overshadowed by genuine curiosity. But why? That's what I don't get. How can simply watching something change its behaviour? Elias sighed, rubbing the back of his neck. Why does this happen? Well, that's the million-dollar question, isn't it? The honest answer is, we don't fully know. We have mathematical models that describe the how, but the why remains elusive. One leading explanation involves the interaction between the observed system and the measuring apparatus, the observer. He paused, gauging Sarah's expression. She looked unconvinced. Let's break that down. To observe something, we need to interact with it. We need to bounce light off it or bombard it with other particles. In the quantum world, these interactions aren't gentle. They're more like a clumsy giant poking at a delicate soap bubble. The interaction itself changes the state of the system. So it's not really observation in the way we think of it, Sarah said slowly. It's more like interference? Exactly, Elias exclaimed, his eyes lighting up. Imagine trying to measure the air pressure in a tyre with a gauge that requires you to release a significant amount of air to get a reading. The act of measuring drastically alters the pressure you were trying to measure in the first place. That's kind of what's happening at the quantum level. He scribbled furiously on the board, drawing a diagram of a tyre and a comically oversized pressure gauge. Sarah considered this. Okay, so observation messes things up. What does this have to do with living forever? Patience, my friend, Elias said, a mischievous grin spreading across his face. We're getting there. The observer effect is a crucial piece of the quantum immortality puzzle because it directly impacts the many worlds interpretation, MWI. Remember, MWI states that every quantum event causes the universe to split into multiple branches, each representing a different possible outcome. He sketched a branching diagram on the whiteboard, the lines diverging endlessly. The core idea behind quantum immortality is that your consciousness always follows the branch where you survive. But how does it choose that branch? This is where the observer effect becomes really interesting. He turned to Sarah, his gaze intense. Consider a scenario where you're facing a 50-50 chance of survival. Maybe you're playing Russian roulette. A terrible idea, by the way. Please don't. In one branch of the universe, the gun fires and you die. In another branch, the gun doesn't fire and you live. According to MWI, both branches exist. Sarah shuddered. That's horrifying. It is, Elias agreed somberly. But from your subjective perspective, you only experience the branch where you survive. You pull the trigger countless times, and each time the universe splits. In the vast majority of those branches, you die. But there's always one branch where you get lucky. And, crucially, that's the only branch you're conscious of. He paused, letting the implication sink in. So, is it really luck? Or is there something more profound going on? Some proponents of quantum immortality suggest that consciousness itself plays a role in collapsing the wave function, or, more accurately in the MWI, following the branch where it continues to exist. Your consciousness, they argue, is the ultimate observer. So you're saying that my will to live somehow forces the universe to bend to my survival? Sarah asked, her voice laced with disbelief. Not exactly forces, Elias clarified. Think of it this way. If consciousness ceases to exist in a particular branch, There's no you to observe that outcome. Therefore, the only outcomes that can be observed and therefore experienced are those where consciousness persists. It's a mind-bending feedback loop. He tapped his head, as if trying to untangle the complex web of ideas within. Now, let's tackle a common objection. If quantum immortality is real, why aren't we all immortal already? Why do people still die? He leaned against the whiteboard, his expression serious. This is a crucial point. Quantum immortality doesn't mean you're immune to all forms of death. It only applies to situations where your death is determined by a quantum event with multiple possible outcomes. Think back to Russian roulette. The firing of the gun is determined by the random decay of radioactive isotopes, which is a quantum process. But if you get hit by a bus, that's a classical macroscopic event. There's no quantum uncertainty involved. The bus hits you, and, well, that's pretty much it. No quantum branching is going to save you from that. He drew a picture of a bus, complete with a cartoonish Grim Reaper standing on the front bumper. Similarly, if you die of old age, that's a gradual process of cellular decay, not a single quantum event with multiple possible outcomes. Quantum immortality isn't a magic shield against the ravages of time or the dangers of the everyday world. He straightened up, his brow furrowed. Furthermore, even in situations where quantum immortality might apply, the jumps between universes could have consequences. Imagine surviving Russian roulette countless times. The universe you end up in might be subtly different from the one you started in. Maybe you're slightly off-center, or maybe the world around you has shifted in ways you don't immediately notice. Elias paused, a faraway look in his eyes. Over time, these small differences could accumulate, leading to a reality that's increasingly bizarre and unrecognizable. You might find yourself in a world where cats talk, or where the sky is green, or where everyone believes pineapple belongs on pizza, a truly horrifying prospect. Sarah laughed, the tension in the room easing slightly. Okay, now you're just being ridiculous. Am I? Elias asked, a hint of a challenge in his voice. So, while quantum immortality might offer a way to cheat death in certain quantum-related scenarios, it's not a free pass to eternal life, and it might come with some unexpected side effects. He stepped back from the whiteboard, surveying his diagrams and equations. What does all this mean for our understanding of reality? Does it mean that consciousness is fundamental, playing an active role in shaping the universe? Or is it simply a passive observer, along for the ride? These are questions that scientists and philosophers are still grappling with. He picked up his coffee cup, now cold and bitter. In the next chapter, we'll explore the philosophical implications of quantum immortality. We'll delve into the nature of consciousness, the meaning of existence, and the ethical dilemmas that arise when we start tinkering with the fabric of reality. Get ready to question everything you thought you knew about life, death, and the universe. It's going to be a wild ride. He took a large gulp of the cold coffee, wincing slightly, but his eyes were already shining with the excitement of the intellectual journey ahead. Okay, so where does this leave us? We've danced around the edges of quantum immortality, seen its reflection in the Schrödinger's cat paradox, and glimpsed its potential through the many worlds interpretation. Now, let's dive headfirst into the philosophical rabbit hole. Because honestly, that's where things get really interesting. I can practically feel the gears grinding in your mind, the questions bubbling to the surface. Trust me, I've been there. Weeks spent staring at the ceiling, contemplating the implications of a potentially infinite existence. It's enough to make anyone question their sanity, or at least their grip on reality. What does it mean to live forever, even if it's only in some branching reality? What does it say about our consciousness, our perception of reality, and the very nature of existence? These aren't just scientific questions anymore. They're deeply philosophical, ethical, and even spiritual. We're talking about the very fabric of being, the fundamental building blocks of what makes us us. Are we just biological machines, destined for oblivion, or is there something more? A spark, a soul, a persistent echo that resonates across the multiverse. Think about it. If every quantum decision point creates a new universe, and in some of those universes you survive, what does that do to the concept of death? Does it diminish it? Does it make it less final? I remember the first time I truly grappled with this idea. It was late, I was fueled by lukewarm coffee and sheer intellectual curiosity, and the thought hit me like a ton of bricks. If death isn't the end, then what is the end? Is there an end, or are we just endlessly branching, endlessly evolving in an infinite tapestry of possibilities? Let's consider a thought experiment. Imagine you're facing a firing squad. Morbid, we know, but bear with us. Each gun is equipped with a quantum trigger. This trigger, when pulled, initiates a quantum event and, say, the decay of a radioactive isotope. If the isotope decays, the gun fires. If it doesn't, the gun remains silent. The air is thick with tension. The smell of gun oil hangs heavy. You can feel the sweat beading on your forehead, the frantic thumping of your heart against your ribs. You try to focus on something, anything, to distract yourself from the impending doom. A bird chirping in the distance, the rough texture of the wooden post you're tied to, the glint of sunlight on the barrels of the rifles. According to MDY and the Quantum Immortality hypothesis, in some universes, the isotope will decay for every gun. And you'll be, well, you won't be having a good day. A wave of nausea washes over you. The world seems to tilt on its axis. You close your eyes, bracing for the inevitable. But in other universes, a statistically improbable event occurs. The isotope fails to decay in at least one of the guns. You survive. Now here's the kicker. From your perspective, experiencing the world through the lens of your consciousness, you will only experience the universes where you survive. You'll never experience the universes where all the guns fire. Why? Because in those universes, you're dead. There's no you left to experience anything. It's a chillingly simple yet profoundly unsettling thought. Imagine the void, the utter nothingness. But you can't, can you? Because if you could, you wouldn't be you anymore. So you might find yourself blinking, staring at a bewildered firing squad. Maybe their guns malfunctioned. Maybe they had a sudden change of heart. Maybe a flock of pigeons flew in front of the bullets at the last second. The reason doesn't matter. What matters is that you survived, and your consciousness continues to flow, pulled along the path of least resistance, the path of survival. You gasp for breath, your lungs burning. You can hear the murmurs of the soldiers, their faces etched with confusion and disbelief. One of them, a young man with wide, frightened eyes, stumbles backward, dropping his rifle. What just happened?" he whispers, his voice trembling. The officer in charge, a grizzled veteran with a stern expression, barks an order. "Reload! Prepare to fire again!" But the thought lingers in your mind. Why me? Why did I survive? Is it just luck? Or is there something more at play? But what happens after that? Do you just keep dodging quantum bullets, living an increasingly improbable life? Does your reality become more and more bizarre as you jump from one near-death experience to another? Imagine a life lived on the razor's edge, a constant dance with death, a life where the laws of probability seem to bend and break around you, creating increasingly outlandish scenarios to keep you alive. A world where you're constantly one step ahead of disaster, a cosmic Houdini escaping from ever more elaborate traps. This brings us to the ethical implications. If quantum immortality is real, does it change our responsibility to ourselves and others? If you know that you'll always survive something, does that make you more reckless? Does it diminish the value of life knowing that death is never truly the end? This is where the philosophical rubber meets the road, where the theoretical becomes deeply personal. Imagine someone who believes in quantum immortality and decides to engage in incredibly risky behavior. They might reason, well, even if this goes wrong, I'll just end up in a universe where it goes right. So what's the harm? I can picture the scene, a daredevil scaling a skyscraper without ropes, a gambler betting their entire life savings on a single roll of the dice, a reckless driver weaving through traffic at breakneck speed. But what about the other people in that universe? What about the potential for suffering and chaos that your actions could cause? Just because you might survive doesn't mean everyone else will. And even if they do, their lives might be drastically altered by your recklessness. A car crash that leaves innocent bystanders injured, a financial collapse that ruins the lives of countless investors, a political stunt that plunges a nation into turmoil. This highlights a crucial point. Quantum immortality, even if true, doesn't absolve us of our ethical responsibilities. We still have a duty to act responsibly, to consider the consequences of our actions, and to minimize harm to ourselves and others. We can't just shrug our shoulders and say, oh well, it'll all work out in some other universe. Because the people in this universe are counting on us to do the right thing. Furthermore, let's consider the nature of consciousness itself. What is it exactly? Is it a fundamental property of the universe, like gravity or electromagnetism? Or is it an emergent phenomenon arising from the complex interactions of matter and energy in the brain? This is the million-dollar question, the holy grail of neuroscience. The answer to this question is crucial to understanding quantum immortality. If consciousness is simply a product of the brain, then when the brain dies, consciousness ceases to exist. End of story. Quantum immortality becomes nothing more than a theoretical curiosity. It's like saying that a computer program can continue to run after the computer has been destroyed. It just doesn't make sense. However, if consciousness is somehow more fundamental, if it exists independently of the physical brain, then the possibility of quantum immortality becomes much more plausible. Perhaps consciousness acts as a kind of quantum observer, influencing the collapse of the wave function and guiding us towards realities where we continue to exist. Maybe our brains are just receivers, tuning into a universal consciousness field. This idea is closely related to the concept of panpsychism, the belief that consciousness is a fundamental property of all matter, not just brains. Panpsychism suggests that even atoms and molecules possess a rudimentary form of consciousness. If this is true, then the universe itself might be conscious, and our individual consciousnesses might be just fragments of this larger cosmic consciousness. Imagine the implications, a universe that is not just a cold, lifeless void, but a living, breathing entity, aware of itself and everything within it. Now we're really getting into deep waters, aren't we? I can almost hear the collective groan of those who prefer their science neatly packaged and easily digestible. But this is where the real fun begins, where we start to question everything we thought we knew about the universe and our place within it. Let's bring it back to something a little more concrete. Remember the double slit experiment? We talked about how the act of observation changes the behavior of electrons, causing them to behave like particles instead of waves. What if consciousness is the observer in this scenario? What if our conscious awareness is what forces the quantum world to choose a particular reality? This is a radical idea, we know. It suggests that our minds are not just passive observers of the universe, but active participants in its creation. It implies that we have a far greater influence over reality than we ever thought possible. It's like saying that we're all co-creators of the universe, shaping reality with our thoughts and intentions. But if this is true, then what are the limits of our influence? Can we consciously choose to jump to different universes? Can we consciously shape our reality to our liking? Can we manifest our desires simply by focusing our minds on them? These are questions that science is only beginning to explore. There are researchers investigating the potential of mind-matter interaction, using techniques like meditation and biofeedback to try to influence quantum systems. The results are often controversial and difficult to replicate, but they offer tantalizing glimpses of the possibility that our minds might have the power to affect the physical world in ways we don't yet understand. I've read studies where experienced meditators seem to be able to subtly influence the output of random number generators, a feat that defies conventional explanation. In the next chapter, we'll delve deeper into these experiments and explore the potential of mind-matter interaction. We'll also examine the criticisms of quantum immortality and the alternative explanations for the phenomena that it attempts to explain. Because, let's be honest, there are plenty of skeptics out there who think this whole idea is just a load of quantum woo, and they might have a point. We'll consider their arguments and see if we can find any common ground. We'll also look at the implications of quantum immortality for our understanding of free will. If our consciousness is guiding us towards certain realities, does that mean we don't have free will? Are we just puppets of the quantum world, being pulled along by the strings of probability? Or do we still have the power to choose our own destiny, even in a multiverse of infinite possibilities? Get ready to question everything you think you know about reality, consciousness, and the meaning of life. It's going to be a wild ride. Fasten your seatbelts, because we're about to go even deeper down the rabbit hole. The adventure has just begun. Okay, let's dive deeper into this quantum rabbit hole. After all, if we're entertaining the possibility of quantum immortality, we need to address the elephant in the room, the critics. Are there gaping holes in the theory? Is it just wishful thinking dressed up in scientific jargon? Let's sharpen our minds and dissect the counter-arguments. One of the most common criticisms levelled against QI revolves around the sheer implausibility of the quantum jumps required. Remember, we're talking about hopping between universes, each a slightly different version of reality where, in our case, we narrowly avoided a quantum-determined death. The argument goes that these jumps, even if theoretically possible, would lead to increasingly bizarre and unrecognizable realities. Think about it. Let's say you survive the initial quantum coin flip that was supposed to trigger a deadly event. Congratulations, you've branched into a universe where you lived. But what about the next quantum event, and the one after that? Each time you're potentially shunted into a reality where the odds of your survival become increasingly improbable. Imagine a scenario where you're constantly avoiding quantum-triggered car accidents. The universe you end up in might be one where cars are incredibly rare, or where roads are designed in such a convoluted way to minimize accidents, or even where you're simply confined to your home to ensure your safety. The cumulative effect of these constant quantum corrections could be a life so drastically different from your original one that it's barely recognizable. You might be alive, but is it really you living that life? This brings us to the problem of predictability. If QI is real, shouldn't we be able to predict to some extent the kinds of universes we're likely to jump into? If we're constantly being steered towards survival, shouldn't there be some observable pattern in the universe around us that reflects this bias? So far, we haven't found any. The universe, as far as we can tell, seems remarkably indifferent to our individual survival. Another major point of contention lies in the assumption that consciousness is somehow aheel, or capable of influencing quantum events. Remember the observer effect. While it's true that observation plays a role in collapsing the wave function, there's no solid evidence to suggest that consciousness is the only or even the primary factor at play. Many physicists argue that any interaction with a quantum system, regardless of whether it involves a conscious observer, will cause decoherence and the collapse of the wave function. A machine, a rock, even a stray photon could act as an observer in this sense. So why should our consciousness be any different? Why would it have the power to steer us towards survival in a way that a simple measuring device couldn't? Furthermore, the link between consciousness and the physical world remains a profound mystery. We still don't fully understand how consciousness arises from the complex interactions of neurons in the brain. To then suggest that this consciousness can somehow influence the fundamental laws of quantum mechanics is a huge leap, one that requires a lot more evidence than we currently have. And what about the people in the universe where you do die? If you jump to another reality, are they simply left behind? Does their experience somehow cease to exist? This raises some unsettling questions about the nature of reality and the value of individual consciousness. Are we essentially abandoning our counterparts in other universes to their fates? Perhaps the most fundamental criticism of QI is that it's simply untestable. Science relies on empirical evidence, on the ability to design experiments that can either support or refute a hypothesis. But how could we ever definitively prove or disprove QI? We can't directly observe other universes, and we can't reliably predict when and where these quantum jumps might occur. Proponents of QI suggest that we might be able to detect subtle anomalies in the universe that could hint at its existence. Perhaps we could find statistical deviations from expected probabilities in certain quantum experiments, or perhaps we could identify patterns in the cosmic microwave background that suggest the influence of other universes. But so far, these attempts have been unsuccessful. So where does this leave us? Are we back to square one? Is QI just a fascinating thought experiment with no basis in reality? Not necessarily. Even if QI is ultimately proven false, the exploration of its implications can still be incredibly valuable. It forces us to confront fundamental questions about the nature of reality, consciousness, and our place in the universe. It challenges us to think beyond the confines of classical physics and to consider the possibility that the universe might be far stranger and more interconnected than we ever imagined. And perhaps most importantly, it reminds us of the preciousness and fragility of life and the importance of making the most of every moment we have. Now let's consider the question of free will. If QI is real, and our consciousness is somehow guiding us towards survival, does that mean we don't have free will? Are we simply puppets dancing to the tune of quantum mechanics? This is a tricky question, and one that philosophers have debated for centuries. On the one hand, if our choices are predetermined by the laws of physics, then it would seem that free will is an illusion. We might feel like we're making conscious decisions, but in reality, our actions are simply the inevitable outcome of a chain of cause and effect. However, some argue that QI actually enhances free will. By constantly branching into new universes, we're creating new possibilities for ourselves. We're not simply following a predetermined path, we're actively shaping our own destiny, albeit on a quantum level. Each decision we make, each action we take, has the potential to create a new branch in the multiverse, a new version of reality where we can explore different possibilities and pursue different goals. Think of it like this. Imagine you're standing at a crossroads. In a classical universe, you can only choose one path, but in a quantum universe, you can choose both paths simultaneously. You branch into two different realities, one where you go left and one where you go right. In each reality, you have the freedom to make further choices and shape your own destiny. So perhaps QI doesn't negate free will, it simply expands its scope. We're not just making choices within a single universe, we're making choices that resonate across the entire multiverse. And that in itself is a pretty mind-blowing thought. But let's not get too carried away with the idea of quantum free will. It's important to remember that even if QI is real, our choices are still constrained by the laws of physics and the circumstances of our lives. We can't simply will ourselves into any universe we desire. We're still bound by the limitations of our physical bodies and the constraints of our environment. Ultimately, the question of free will and QI is a matter of perspective. It depends on how you define free will and how you interpret the implications of quantum mechanics. There is no easy answer, and it's likely that the debate will continue for many years to come. In the next chapter, we'll explore the ethical implications of QI in more detail. What does it mean to live in a multiverse where our choices have potentially infinite consequences? Does QI give us a greater responsibility to ourselves and to others? And how should we approach the prospect of quantum immortality, if it's even possible? Let's keep digging. So we've journeyed through the mind-bending landscape of quantum immortality, explored the many worlds interpretation, and even wrestled with the criticisms. But let's not shy away from the elephant in the room, or rather, the infinitely branching herd of elephants in infinitely branching rooms, the ethical implications. If a version of you survives every near-death experience, what does that mean for how we live, how we treat ourselves, and perhaps most importantly, how we treat others? Think about it. If your subjective experience always continues down the path of survival, does it diminish the value of life? Does it make risk-taking more acceptable? Does it change our moral compass? Let's consider a classic ethical dilemma. The trolley problem. You're standing next to a lever. A trolley is hurtling down a track towards 5 people. If you pull the lever, the trolley will switch to a different track, saving the 5 but killing 1 person on that track. What do you do? In a normal universe, the decision is agonizing. You weigh the consequences, the potential guilt, the moral implications of action versus inaction. But what if quantum immortality is real? Does the equation change? Perhaps you reason. Well, in one branch I do nothing and 5 people die, in another I pull the lever, 1 person dies, but I survive in both. So pulling the lever is the objectively better choice because a version of a me gets to continue experiencing reality. Creepy, right? But let's dial up the creepiness. What if you knew you were in a quantum immortality scenario? Imagine you're a soldier facing a suicide mission. In a conventional universe, it's a tragic sacrifice. But with QI you might think, okay, in most branches I die heroically. But there's got to be at least one branch where I miraculously survive, becoming an even bigger hero. Does that make you more willing to volunteer? Does it make the decision-making process less human? The potential for abuse is staggering. Imagine a totalitarian regime that believes in quantum immortality. They might rationalize sacrificing dissidents, believing that a version of those dissidents will always survive in some reality, therefore mitigating the ethical weight of their actions. Don't worry, they might say, dripping with sinister condescension. A part of you will live on. Now, step into the quantum execution chamber. Yikes. And it's not just about grand, sweeping ethical violations. Think about everyday decisions. Do you drive more recklessly, figuring that in some branch you'll avoid the accident? Do you neglect your health, figuring that in some branch you'll miraculously recover from that terminal illness? Does the concept of quantum immortality breed complacency, a dangerous disregard for the fragility of life, even if it's only the fragility of other versions of life? Sarah, I see you're looking skeptical. I know, it's a lot to swallow. You're probably thinking, this is all hypothetical. We don't know quantum immortality is real. And you're right. We don't. But that's precisely why it's so important to consider these ethical implications now. Because if even a possibility exists, even a theoretical framework that suggests the potential for continued subjective experience beyond conventional death, then we have a responsibility to grapple with the consequences. Think of it like this. We debate the ethics of artificial intelligence, even though true AI is still largely theoretical. We consider the implications of genetic engineering, even though the technology is still in its early stages. We do this because foresight is crucial. We need to be prepared for the potential ethical minefields that new discoveries might create. Quantum immortality is no different. Elias, what are your thoughts on this? How do you reconcile the seemingly deterministic nature of quantum mechanics with the concept of free will, especially in the context of ethical decision-making? Elias. That's the million-dollar question, Sarah. The interplay between quantum mechanics and free will is one of the most perplexing and hotly debated topics in physics and philosophy. If every quantum event creates a branching universe, and our actions are ultimately determined by quantum events, then are we truly free? Or are we just puppets dancing to the tune of quantum probabilities? Some argue that free will is an illusion, a comforting narrative we tell ourselves to make sense of a chaotic world. Others believe that consciousness plays a role in collapsing the wave function, in selecting which branch of reality we experience. In that case, our choices, even if influenced by quantum probabilities, still have a meaningful impact. But even if free will is an illusion, does that negate our ethical responsibilities? I would argue no. Even if our actions are predetermined, they still have consequences for ourselves and for others in our perceived reality. And if quantum immortality is real, those consequences extend across multiple realities, affecting countless versions of ourselves and others. So whether we're truly free or not, we still have a moral imperative to act in a way that minimizes suffering and maximizes well-being across all possible realities. It's a daunting task, but one we can't afford to ignore. Let's bring this back to something a little more tangible. Let's talk about experiments. As we discussed before, direct proof of quantum immortality is likely impossible, but can we explore the fringes of this concept? Can we design experiments that probe the relationship between consciousness and quantum events, even if they don't definitively prove or disprove the MWI? The answer, perhaps surprisingly, is yes. There's a growing field of research exploring the potential for mind-matter interaction. Now, before you conjure images of spoon-bending psychics, let's clarify. We're not talking about bending metal with our minds. We're talking about subtle, statistical influences on quantum systems. Remember the double-slit experiment? Electrons, when not observed, pass through both slits simultaneously, creating an interference pattern. But when observed, they behave like particles, passing through only one slit. What if we could design an experiment where a participant attempts to influence which slit the electron passes through, not through any physical means, but through focused intention? Several researchers have attempted variations of this. The results are inconclusive. Some studies have shown statistically significant deviations from chance, suggesting a possible influence of consciousness on quantum events. Others have found no effect. The field is fraught with methodological challenges, including the difficulty of isolating consciousness as a variable and the potential for experimenter bias. But the very fact that these experiments are being conducted is significant. It shows a willingness to explore the boundaries of our understanding, to question the conventional wisdom that consciousness is merely a byproduct of physical processes. Now let's be clear. Even if these experiments were to consistently demonstrate a statistically significant effect, it wouldn't prove quantum immortality, but it would provide evidence that consciousness can interact with the quantum world in ways we don't currently understand, and that in itself would be a profound discovery, potentially revolutionizing our understanding of reality and our place within it. And what about the ethical implications of those kinds of experiments? If we discover that consciousness can influence quantum events, even in a small way, what responsibilities do we have to control and regulate that influence? Could such knowledge be used for good, to heal the sick or enhance human potential? Or could it be used for nefarious purposes, to manipulate and control others? These are questions we need to start asking now, before the technology outpaces our ethical frameworks. Because the future, as always, is uncertain. But one thing is clear: the exploration of quantum mechanics, consciousness, and the potential for quantum immortality is not just a scientific endeavor. It's a philosophical, ethical, and ultimately a human one. In the next chapter, let's delve into some specific experimental designs and the challenges of interpreting the results. We'll also explore the philosophical implications of a universe where consciousness plays a more active role in shaping reality. Get ready to have your minds bent even further. So where does all this leave us? We've built this, let's call it a rather ambitious theoretical framework. We've entertained the possibility of quantum immortality, wrestled with its philosophical paradoxes, and even peeked into the ethical minefield it might create. But theory, however elegant, needs to face the music. It needs to confront reality, or at least attempt to. That means experiments. But how do you even begin to test something as outlandish as quantum immortality? You can't exactly run a controlled trial on dying and hopping to alternate realities. Please don't try. What we can do, however, is explore the possibility of mind-matter interaction at the quantum level. If consciousness does play a role in collapsing the wave function, as some interpretations suggest, then perhaps we can design experiments to detect this influence. Think back to the double-slit experiment, that cornerstone of quantum weirdness. We remember how particles, like electrons, pass through both slits simultaneously as a wave, creating an interference pattern on the detector screen. But when we try to observe which slit the electron goes through, the wave function collapses and the electron behaves like a particle, passing through only one slit and destroying the interference pattern. Now, imagine modifying this experiment. Instead of a mechanical detector, what if we introduced a conscious observer, attempting to mentally influence which slit the electron passes through? Could a focused intention, a directed thought, subtly alter the probabilities, nudging the electron one way or the other? This is the basic idea behind a class of experiments exploring what's often called mind-matter interaction, or distant mental influence. They're incredibly controversial, and the results are, well, let's just say they're not exactly conclusive. Let's consider one hypothetical and simplified experimental design. You have a standard double-slit setup, but instead of a simple on-off detector, you have a more sophisticated system that records the position of each electron as it hits the screen. You also have a volunteer sitting in a shielded room focusing their attention on the experiment. During some runs, the volunteer is instructed to try to make the electrons go through the left slit. During other runs, they try to make them go through the right slit. And during control runs, they simply relax and don't try to influence anything. What are we looking for? If consciousness has an effect, we might see a subtle shift in the interference pattern, maybe a slight increase in the number of electrons hitting the screen directly behind the slit the volunteer is focusing on. It wouldn't be a dramatic change, mind you. We're talking about potentially tiny deviations from the expected probabilities. Now, the crucial part, rigorous statistical analysis. Any observed effect, no matter how small, needs to be statistically significant. That means running the experiment hundreds, even thousands of times, and carefully analysing the data to rule out chance fluctuations. This is where many of these experiments run into trouble. The problem is, the effects, if they exist at all, are incredibly small. This means you need a huge amount of data to reach statistical significance. And even then, there's always the possibility of confounding variables, subtle factors that you haven't accounted for that could be influencing the results. Maybe the experimenter unconsciously treats the volunteer differently, depending on which condition they're in. Maybe there are subtle electromagnetic fluctuations in the room that correlate with the volunteer's intention. Controlling for these variables is incredibly difficult, and it's one of the main reasons why these experiments are met with so much skepticism from the scientific community. Replicability is also a massive issue. Even if one lab reports a positive result, it needs to be independently replicated by other labs before it can be taken seriously. And unfortunately, many of these experiments have failed to replicate. So, what are we to make of all this? Are these experiments a dead end? Are we chasing ghosts in the quantum machine? Not necessarily. Even if the effects are small and difficult to detect, they could still be real, and even if they are not directly related to quantum immortality, they could still tell us something profound about the nature of consciousness and its relationship to the physical world. Let's say for the sake of argument that these experiments do eventually yield consistent, replicable evidence of mind-matter interaction at the quantum level. What would that even mean? Well, it would certainly throw a wrench into our conventional understanding of physics. It would suggest that consciousness is not merely a passive observer of reality, but an active participant in its creation. This would have profound implications for our understanding of free will. If our thoughts and intentions can influence the behavior of quantum systems, then perhaps we have more agency over our reality than we previously thought. Maybe our choices, our desires, our very beliefs subtly shape the universe around us. Of course, this also raises some unsettling questions. If consciousness can influence quantum events, then whose consciousness is doing the influencing? Is it just our individual consciousness? Or is there some kind of collective consciousness at play? Are we all interconnected in some way, subtly influencing each other's realities? And what about the ethical implications? If our thoughts can have real-world effects, then are we responsible for the consequences of our thoughts, even if they're unintentional? Could negative thoughts like hatred or anger somehow manifest in negative outcomes? It's a slippery slope, and one we need to tread carefully. Sarah, our resident biologist, would likely point out the sheer improbability of all this. "Come on," she might say. "You're suggesting that our minds can somehow manipulate the fundamental laws of physics. That sounds like something out of a science fiction movie." And she'd have a point. It does sound far-fetched. But remember, quantum mechanics itself is far-fetched. It's a theory that defies our everyday intuition, that challenges our most basic assumptions about the nature of reality. So perhaps it's not so unreasonable to consider the possibility that consciousness might play a role in this strange and wonderful quantum world. Even if we never find definitive proof of quantum immortality, the quest to understand the relationship between consciousness and quantum mechanics is a worthwhile endeavor in itself. It forces us to confront the deepest mysteries of existence. What is consciousness? What is reality? And what is our place in the universe? We've danced around the edges of neuroscience, haven't we? Let's bring it into the conversation more directly. If consciousness is intertwined with quantum phenomena, then surely there must be some reflection of this within the very structure and function of the brain. Are there quantum processes occurring within our neurons, within our synapses, that somehow give rise to conscious experience? This is the realm of quantum biology, a relatively new and rapidly growing field that seeks to explore the role of quantum mechanics in biological systems. And while it's still in its early stages, some fascinating discoveries are being made. For example, consider the phenomenon of photosynthesis. Plants are incredibly efficient at converting sunlight into energy, and it turns out that quantum coherence, that weird quantum effect where particles can exist in multiple states simultaneously, plays a crucial role in this process. Energy from sunlight can explore multiple pathways simultaneously within the plant's light harvesting complexes, finding the most efficient route to the reaction center where photosynthesis takes place. This suggests that quantum mechanics is not just some abstract theory that applies to subatomic particles. It's a fundamental part of the natural world influencing even the most complex biological processes. So could quantum coherence also be playing a role in the brain? Could it be involved in the formation of thoughts, the storage of memories, or even the generation of consciousness itself? Some researchers believe so. They point to the fact that the brain is an incredibly noisy environment, full of electromagnetic fields and random fluctuations, and yet somehow it manages to maintain a high degree of order and coherence. Perhaps quantum coherence is the key to this ability. One particularly intriguing idea is that microtubules, tiny structures inside our neurons, might be capable of supporting quantum coherence. These microtubules are like miniature scaffolding, providing structural support for the cell. But some scientists believe they may also act as quantum waveguides, allowing quantum information to travel within the brain. This is the basis of the Ochoa theory, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They suggest that consciousness arises from quantum computations occurring within microtubules. According to their theory, these quantum computations are governed by the laws of quantum mechanics and are influenced by the structure of space-time itself. It's a bold and controversial idea, and it's far from being proven. But it highlights the growing recognition that quantum mechanics may play a far more significant role in biology, and particularly in the brain, than we ever imagined. Where do we go from here? We'll need to delve deeper into the experimental evidence for quantum effects in the brain. We'll need to explore the Ochoa theory in more detail and examine the criticisms that have been levelled against it. And we'll need to grapple with the philosophical implications of a quantum theory of consciousness. Because if consciousness is indeed a quantum phenomenon, then the implications for our understanding of reality, of free will, and even of quantum immortality are truly mind-boggling. Okay, so we've dipped our toes into the strange waters of quantum biology, specifically looking at the possibility that quantum mechanics plays a role in consciousness. We introduced the Ochoa theory, which, as you'll recall, posits that microtubules within our neurons act as quantum computers, and that moments of conscious awareness occur when these microtubules reach a threshold for quantum coherence and collapse. Now, Sarah, I see that skeptical glint in your eye. What's on your mind? Elias, she says, leaning forward. While I appreciate the, shall we say, creative thinking behind Ochoa, it faces some pretty serious hurdles. The brain is a warm, wet, and noisy environment. Quantum coherence is incredibly fragile and typically only survives for extremely short periods at extremely low temperatures. How can it possibly be sustained within microtubules long enough to have any meaningful effect on consciousness? Excellent question, Sarah. This is precisely the central criticism levelled against the Ochoa theory. Critics argue that the brain's environment is far too chaotic for delicate quantum states to maintain coherence. Any interaction with the surrounding environment, a collision with another molecule, a stray photon, would cause decoherence, collapsing the quantum state and destroying any potential quantum computation. So how do proponents of Ochoa respond to this? Well, Penrose and Hameroff, the architects of the theory, propose several mechanisms that could potentially protect microtubules from decoherence. Firstly, they suggest that the structure of microtubules themselves provides a degree of protection. The hollow core of the microtubule, along with the specific arrangement of tubulin proteins, may shield quantum states from external noise. Think of it like a Faraday cage, but for quantum information. It's not perfect, but it could significantly reduce the rate of decoherence. Secondly, they argue that the specific type of quantum coherence involved in Ochoa, specifically quantum entanglement, may be more robust than previously thought. Entanglement, as we discussed earlier, is the bizarre phenomenon where two or more particles become linked, sharing the same fate regardless of the distance separating them. Penrose and Hameroff suggest that entanglement within microtubules could create a network of interconnected quantum states that are more resistant to decoherence than individual isolated states. Thirdly, and this is where things get even more speculative, they propose that some unknown physical mechanism, perhaps related to quantum gravity, might be at play, actively protecting quantum coherence within microtubules. This is, admittedly, the most controversial aspect of the theory, as it invokes physics beyond our current understanding. Now, I know what you're thinking. This sounds like a lot of hand-waving, and you're not entirely wrong. The exact mechanisms by which microtubules could maintain quantum coherence in the brain are still poorly understood and remain a subject of intense debate. There's a significant lack of direct experimental evidence to support these claims. But let's not dismiss the possibility entirely. Remember, the field of quantum biology is still in its infancy. We're only just beginning to explore the potential role of quantum mechanics in biological systems. And as our experimental techniques improve, we may uncover new evidence that supports or refutes the Ocho theory. What kind of evidence are we talking about, Elias? What would it take to actually prove that quantum mechanics is involved in consciousness? Another excellent question. Well, ideally, we'd need to directly observe quantum coherence within microtubules in a living brain. This is an incredibly challenging task, given the size and complexity of the brain and the fragility of quantum states. However, there are some promising avenues of research. One approach involves developing more sensitive techniques for measuring quantum coherence. Researchers are working on new types of microscopes and sensors that can detect subtle quantum signals within biological systems. These techniques could potentially be used to probe the quantum state of microtubules in vitro and eventually in vivo. Another approach involves studying the effects of anesthetics on quantum coherence. Anesthetics are known to disrupt consciousness, and some researchers believe that they may do so by interfering with quantum processes in the brain. By studying how anesthetics affect quantum coherence in microtubules, we might gain insights into the role of quantum mechanics in consciousness. A third approach involves exploring the connection between consciousness and quantum entanglement. Some researchers have proposed that consciousness arises from the entanglement of quantum states across different parts of the brain. If this is true, then we might be able to detect evidence of entanglement by measuring correlations between neural activity in different brain regions. However, even if we were to find direct evidence of quantum coherence in the brain, that wouldn't necessarily prove that it's responsible for consciousness. Correlation does not equal causation, as they say. We would also need to demonstrate that disrupting quantum coherence leads to a loss of consciousness, and that restoring quantum coherence restores consciousness. This is a much more difficult task, but it's essential if we want to establish a causal link between quantum mechanics and consciousness. So where does this leave us? Well, the Ocho theory remains a highly speculative and controversial idea, but it's also a fascinating and thought-provoking one. It challenges our conventional understanding of consciousness and opens up new avenues of research into the relationship between the mind and the quantum world. And then, of course, it has implications for our discussion of quantum immortality. If consciousness is indeed a quantum phenomenon, then the possibility of it hopping to parallel universes to avoid death becomes perhaps a little less far-fetched. But before we get too carried away with the implications of a quantum theory of consciousness, let's take a step back and consider the philosophical implications. If consciousness is indeed a quantum phenomenon, what does that mean for our understanding of reality, of free will, and even of quantum immortality itself? Think about it. If our conscious experiences are ultimately rooted in the probabilistic nature of quantum mechanics, does that mean that our thoughts and actions are not entirely our own? Are we simply puppets of quantum chance, our lives dictated by the random fluctuations of quantum fields? And what about free will? If our brains are essentially quantum computers, then are our decisions predetermined by the laws of quantum mechanics? Or does the inherent uncertainty of quantum mechanics somehow allow for genuine freedom of choice? These are profound and difficult questions, and there are no easy answers. But they're questions that we need to grapple with if we want to truly understand the nature of consciousness and its relationship to the quantum world. Sarah, I can see you're practically bursting to say something. What's your take on all this? Elias, she says, shaking her head. You're venturing into territory that's even more speculative than quantum biology, if that's even possible. You're talking about the very foundations of reality, of free will, of what it means to be human. And you're basing it all on a theory that, let's be honest, is still largely unproven. I understand your skepticism, Sarah, I reply. But that's precisely why we need to explore these ideas. We can't shy away from the big questions just because they're difficult or uncomfortable. The history of science is full of examples of radical ideas that were initially met with skepticism but eventually revolutionized our understanding of the world. But there's a difference between a radical idea that's supported by evidence and a radical idea that's based on speculation, she counters. And right now, the quantum theory of consciousness is firmly in the latter category. Perhaps, I can see, but that doesn't mean we shouldn't pursue it. We need to keep an open mind to continue exploring the possibilities and to gather as much evidence as we can. Who knows? Maybe one day we'll have a complete and comprehensive understanding of consciousness, one that integrates quantum mechanics, neuroscience, and philosophy. And maybe, just maybe, that understanding will shed light on the mysteries of quantum immortality. And on that note, let's bring in a fresh perspective. We've got Dr. Anya Sharma joining us next week, a neuroscientist specializing in the study of consciousness. She'll offer a grounded perspective, likely pouring cold water on some of our more outlandish ideas. But that's exactly what we need to keep this exploration honest. She'll discuss the current state of consciousness research from a purely neurological perspective, giving us a baseline to compare our quantum ramblings against. Then we'll really get into the nitty-gritty of how these fields might or might not connect. Get ready for a clash of paradigms. Okay, let's delve deeper into the fascinating and often perplexing world of consciousness. We've spent a good deal of time swimming in the theoretical ocean of quantum mechanics, exploring wave functions, superpositions, and the mind-bending implications of the many worlds interpretation. We've wrestled with the idea that every quantum decision spawns a new universe, a reality branching off from our own like the limbs of an infinite tree. But now, let's bring things back down to earth, or rather, back to the intricate folds of the human brain. Because let's be honest, all this talk of quantum immortality, the tantalizing, almost unbelievable notion that consciousness somehow persists across branching universes, dodging death in an endless game of cosmic roulette, hinges on one crucial and still largely unanswered question. What is consciousness, anyway? Is it merely a byproduct of complex neural activity, a sophisticated illusion woven by the billions of neurons firing in our skulls, a biological symphony played out on the instrument of the brain? Some theories suggest, is it something more fundamental, a property of reality itself, perhaps even playing a role in shaping the quantum world? A cosmic constant like gravity or the speed of light, but experienced subjectively? The chasm between these two perspectives is vast, a gulf separating the tangible world of neurons and synapses from the ethereal realm of quantum probabilities. And to bridge that gap, or at least attempt to, we need to hear from the experts on both sides. To get a more grounded perspective, we're going to talk to Dr. Anya Sharma. Dr. Sharma is a neuroscientist at the forefront of consciousness research, a woman who has dedicated her life to understanding the biological underpinnings of thought and experience. She studies the brain, not through the lens of quantum physics and its probabilistic interpretations of reality, but through the meticulous observation of neural circuits, chemical signals, and the complex dance of electrical activity that gives rise to our thoughts, feelings, and perceptions. She's a cartographer of the mind, mapping the intricate pathways that connect stimulus to sensation, memory to meaning. Now, you might be thinking, okay, great. A neuroscientist, she can tell us about brain scans and neurotransmitters. But what does she have to say about quantum immortality? Isn't that outside her area of expertise? Well, that's precisely what we're going to find out. Because while quantum physicists may be comfortable discussing branching universes and the observer effect, casually invoking concepts that defy everyday intuition, neuroscientists like Dr. Sharma tend to operate within a more, shall we say, conventional framework. They focus on the tangible, the measurable, the things they can see and manipulate in the lab. They're the plumbers of the brain, fixing the leaks and rerouting the pipes, not contemplating the nature of the water itself. Let's imagine we're sitting in Sharma's office. It's a bright, sterile space filled with the hum of computers and the faint scent of formaldehyde, a smell that speaks of preserved specimens and countless hours spent dissecting the mysteries of the nervous system. Brain scans adorn the walls, glowing with colourful patterns of activity, each a unique fingerprint of a living mind. Some show the intricate dance of neurons during a simple task like reading a word. Others reveal the chaotic storm of activity during a seizure. Dr. Sharma, a woman with a sharp intellect and a no-nonsense demeanour, sits across from us, behind a large uncluttered desk. Her dark hair is pulled back in a practical bun, and her eyes, magnified by wire-rimmed glasses, hold a sceptical glint. She's wearing a crisp white lab coat, and her hands, resting calmly on the desk, are those of someone accustomed to precision and control, who exudes an aura of quiet authority, the confidence of someone who has spent years grappling with the most complex object in the known universe. "Quantum immortality," she says, the words measured and deliberate, leaning back in her chair. "It's an interesting thought experiment, I'll give you that. It certainly sparks the imagination. But from a neurological perspective, it raises a lot of red flags." She pauses, her gaze unwavering. "Serious red flags." "Red flags? Like what?" we ask, leaning her forward, eager to hear her perspective to understand the neurological challenges that quantum immortality presents. "Well, for starters," she replies, "the brain is incredibly fragile. It's exquisitely sensitive to even the slightest disruptions. A lack of oxygen for just a few minutes, a blow to the head, a chemical imbalance. Any of these things can cause irreversible damage, leading to cognitive impairment, personality changes, or even death." She gestures towards a brain scan on the wall, a stark image showing the devastating effects of a stroke. "Look at this. This patient suffered a relatively minor stroke, and yet their ability to speak has been permanently impaired. How can consciousness jump to another universe if the very hardware that supports it is so easily damaged?" "But what if," we interject, attempting to reconcile the neurological perspective with the quantum one, the many worlds interpretation is correct? What if, in the universe where the brain is irreparably damaged, consciousness simply shifts to another universe where it survives? A universe where the stroke never happened, or where the damage is less severe? Dr. Sharma sighs, a hint of exasperation in her voice. "That's a big what if, isn't it? And it requires a leap of faith that frankly goes against everything we know about the brain. We have decades of research showing a direct correlation between brain activity and conscious experience. Damage the brain and you damage consciousness. It's as simple as that." She taps her finger on the desk for emphasis. "We can literally watch consciousness fade away as brain function declines. It's not some abstract concept, it's a tangible phenomenon that we can observe and measure." She continues, "The idea that consciousness can somehow jump to another universe to avoid death implies that consciousness is independent of the brain, that it's some kind of fundamental entity that exists outside of the physical world. A soul, perhaps, but there's absolutely no evidence to support that claim. In fact, all the evidence points in the opposite direction. Consciousness is an emergent property of the brain, a product of its complex organization and activity. This is a crucial point. If consciousness is simply an emergent property, like the whirring of a computer fan, then destroying the computer also destroys the whirring. There's nothing left to jump anywhere. The music stops when the instrument breaks. The flame is extinguished when the candle is consumed. What about the Ochoa theory, we ask, referring to the controversial idea proposed by Sir Roger Penrose and Stuart Hameroff that microtubules within neurons act as quantum computers, potentially providing a link between quantum mechanics and consciousness. Could these microscopic structures be the conduits through which consciousness might navigate the multiverse? Dr. Sharma raises an eyebrow. Orch-OR is a fascinating hypothesis, but it's still highly speculative. The evidence supporting it is weak, and there are many serious challenges to overcome. For example, how can quantum coherence be maintained within the warm, wet, and noisy environment of the brain? She shakes her head slightly. The brain is a biological soup, not a cryogenically cooled quantum computer. She explains that maintaining quantum coherence, the delicate state of superposition that allows quantum computers to perform their calculations, is incredibly difficult. Any interaction with the environment can cause decoherence, collapsing the superposition and destroying the quantum effects. The brain, with its constant electrical activity and chemical reactions, seems like the least likely place to find sustained quantum coherence. It's like trying to maintain a delicate sandcastle in the middle of a hurricane. Furthermore, Dr. Sharma adds, even if microtubules do exhibit quantum behavior, it's not clear how that would give rise to consciousness. We still need to understand how these quantum processes could generate subjective experience, the feeling of what it's like to be conscious. How does quantum entanglement translate into the redness of red, the feeling of joy, the memory of a loved one? She pauses, taking a sip of water from a glass on her desk. Look, I understand the appeal of quantum immortality. It's a comforting idea, the notion that we can somehow cheat death, that our consciousness will somehow persist beyond the limitations of our physical bodies. But we need to be realistic. The brain is a complex and delicate organ, and when it dies, consciousness ceases to exist. That's the hard truth as far as we can tell. Her voice is firm but not unkind. It's the voice of someone who has seen death up close, who has witnessed the slow fading of consciousness in countless patients. Dr. Sharma's perspective is a stark contrast to the more speculative views we've explored so far. She represents the voice of conventional neuroscience, grounded in empirical evidence and skeptical of grand, overarching theories. She's the pragmatist, the empiricist, the one who insists on seeing the evidence before accepting the conclusion. But does this mean that quantum immortality is simply wishful thinking? Not necessarily. It's important to remember that our understanding of consciousness is still incomplete. There are many mysteries that remain unsolved. We've only scratched the surface of this vast and complex landscape. And perhaps, just perhaps, there is a deeper connection between quantum mechanics and consciousness than we currently understand. Perhaps the brain is more than just a biological computer. Perhaps it's a receiver, a transducer, tuning into a reality that transcends our current understanding. Maybe the key lies in understanding how information is processed and integrated within the brain. How do billions of individual neurons, each firing in its own way, create a unified, coherent experience of the world? How does the brain transform a jumble of electrical signals into the rich tapestry of our conscious experience? What is the neural correlate of consciousness, the specific pattern of brain activity that corresponds to a particular conscious experience? What is the physical signature of a thought, a feeling, a memory? These are the questions that drive Dr. Sharma's research, and they're the questions that will ultimately determine whether quantum immortality is a plausible possibility or just a fascinating fantasy. The answers, if they exist, are buried deep within the intricate workings of the brain, waiting to be discovered. In the next chapter, we'll delve deeper into the neuroscience of consciousness, exploring different theories of how the brain gives rise to subjective experience. We'll look at the integrated information theory, which proposes that consciousness is related to the amount of integrated information in a system, and the global workspace theory, which suggests that consciousness arises when information is broadcast throughout the brain. We'll also examine the role of attention, memory, and perception in shaping our conscious experience. We'll explore the neural circuits that underpin our sense of self, our ability to experience emotions, and our capacity for abstract thought. And as we explore these different perspectives, we'll keep in mind the question that has been driving our exploration all along. Could quantum mechanics play a role in the emergence of consciousness? And could that role have implications for our understanding of life, death, and perhaps even immortality? The journey continues, and the destination remains uncertain. But one thing is for sure, the quest to understand consciousness is one of the most fascinating and important challenges facing science today. It's a quest that will require the combined efforts of physicists, neuroscientists, philosophers, and perhaps even artists and poets to unlock the secrets of the human mind. Dr. Sharma's skepticism hangs heavy in the air, a necessary counterpoint to the heady speculation we've been indulging in. The allure of quantum immortality is undeniable, but can we truly reconcile it with what we know about the messy, intricate reality of the brain? Let's ground ourselves, then, in the established theories of consciousness that neuroscience offers. Forget for a moment branching universes and observer effects. Instead, think of the brain as a vast interconnected network, a symphony orchestra composed of billions of neurons, each playing its part in the grand composition of conscious experience. How do these individual notes combine to create the rich tapestry of our awareness? That's the question these theories attempt to answer. One prominent theory is integrated information theory, IIT. Proposed by Giulio Tononi, IIT suggests that consciousness isn't just about what information is being processed, but how integrated that information is. The more integrated and complex a system is, the more conscious it is. Think of it this way. A simple light switch has very little integrated information. It's either on or off. Your brain, on the other hand, is constantly combining sensory input, memories, emotions, and abstract thoughts into a unified, seamless experience. The key concept in IIT is phi, F, which represents the amount of integrated information a system possesses. The higher the phi, the higher the level of consciousness. A rock, according to IIT, would have a very low phi, while a human brain would have a very high phi. But here's the kicker. IIT doesn't necessarily restrict consciousness to biological systems. Theoretically, a sufficiently complex and integrated computer could also be conscious. Does this mean your smartphone secretly yearns for a software update? Probably not, but IIT forces us to consider what fundamental properties are necessary for consciousness to arise. It shifts the focus from the stuff that makes up the system, neurons, silicon chips, to the structure of the information processing itself. Another influential theory is global workspace theory, GWT, championed by Bernard Baars. GWT posits that consciousness is like a global workspace, a central stage where information from different parts of the brain is broadcast and made available to the rest of the system. Imagine a theatre. Different actors, specialized brain regions, are constantly vying for attention, presenting their information on the central stage, the global workspace. The information that wins out, the loudest actor, so to speak, becomes consciously accessible. So you're walking down the street, your visual cortex is processing the sights, your auditory cortex is processing the sounds, and your motor cortex is controlling your movements. But only a small fraction of this information enters your conscious awareness. According to GWT, this is because only a select few representations, the most salient or relevant pieces of information, are broadcast to the global workspace, allowing you to consciously perceive the scene and navigate your surroundings. What determines which information gets broadcast? Attention plays a crucial role. We consciously attend to things that are important to us, whether it's a potential threat, a familiar face, or a captivating idea. Attention acts as a spotlight, highlighting certain information and amplifying its signal, making it more likely to win the competition for access to the global workspace. Memory is also essential. Our past experiences shape our present perceptions. We interpret the world through the lens of our memories, and these memories influence what we attend to and what we consciously experience. If you've had a bad experience with dogs in the past, you're more likely to pay attention to dogs in your environment and feel a sense of unease. And what about perception? How do our brains transform raw sensory data into meaningful experiences? Perception is not a passive process. It's an active construction. Our brains are constantly making predictions about the world and testing these predictions against sensory input. This process, known as predictive coding, allows us to efficiently process information and anticipate future events. Think about optical illusions. They reveal how our brains actively construct our perception of reality, often filling in gaps and making assumptions based on prior knowledge. The fact that we can be so easily fooled highlights the active, interpretive nature of perception. But where in the brain does all this happen? What are the neural circuits that underpin our sense of self, our emotions, and our conscious awareness? Neuroscientists have identified several key brain regions that are thought to be critical for consciousness. The prefrontal cortex, located at the front of your brain, is involved in higher-level cognitive functions such as planning, decision-making, and working memory. It's often considered the executive control center of the brain, responsible for coordinating and integrating information from different brain regions. The parietal cortex, located behind the frontal lobe, plays a crucial role in spatial awareness, attention, and self-awareness. Damage to the parietal cortex can lead to bizarre neurological conditions such as neglect syndrome, where patients are unaware of one side of their body or the world. The anterior cingulate cortex, ACC, located deep within the frontal lobe, is involved in error detection, conflict monitoring, and emotional regulation. It's thought to play a key role in our subjective experience of emotions and our ability to adapt to changing circumstances. And let's not forget the thalamus, a small but mighty structure located in the center of the brain. The thalamus acts as a relay station, routing sensory information from the body to the cortex. It's also thought to play a role in regulating sleep and wakefulness, which are intimately linked to consciousness. These brain regions, and many others, work together in complex and dynamic ways to give rise to our conscious experience, but the precise mechanisms by which they do this remain a mystery. And that brings us back to our central question. Could quantum mechanics play a role in this neural symphony? Could quantum processes be involved in the emergence of consciousness? And could that role have implications for quantum immortality? Dharma would likely argue that while quantum mechanics undoubtedly governs the behavior of atoms and molecules within the brain, there's no compelling evidence that it plays a significant role in higher-level cognitive functions like consciousness. She might point to the fact that the brain is a warm, wet, and noisy environment, hardly conducive to the delicate quantum phenomena that underpin theories like OR. Decoherence, the process by which quantum coherence is lost due to interactions with the environment, would quickly destroy any quantum effects in the brain, rendering them irrelevant. However, some researchers continue to explore the possibility that quantum mechanics may play a more subtle but significant role in consciousness. They argue that even if quantum effects are short-lived and localized, they could still have a cascading effect on neural activity, influencing the flow of information and shaping our conscious experience. For example, some researchers have proposed that quantum entanglement, the spooky action at a distance that Einstein famously derided, could allow for instantaneous communication between different parts of the brain, bypassing the limitations of classical neural transmission. Others have suggested that quantum tunneling, the ability of particles to pass through barriers that they shouldn't be able to, could facilitate the formation of new neural connections, allowing for rapid learning and adaptation. These are speculative ideas, to be sure, and they face significant challenges. but they highlight the ongoing quest to understand the relationship between quantum mechanics and consciousness. Are we simply complex classical machines, or is there something more, something fundamentally quantum at the heart of our being? Perhaps the answer lies not in choosing one side or the other, but in finding a way to integrate both perspectives. Perhaps consciousness emerges from the interplay between classical and quantum process, with each level of description providing a complementary perspective on the same underlying reality. In the next chapter, we'll delve deeper into the experimental attempts to find this connection, looking at specific studies that explore the potential role of quantum mechanics in brain function and consciousness. We will also revisit the implications of these findings for the possibility of quantum immortality. Are we on the verge of unlocking the secrets of eternal life, or are we chasing a phantom born of wishful thinking and quantum weirdness? Let's find out.